So today we're going to be exploring plate tectonics with Google Earth. The first thing we're going to do is launch Google Earth directly from the web. We don't need to install anything or download anything, nothing. We're just going to launch it. On this page, there's two different launch buttons. One is right below my image. The other one's right up here. They're going to take you to the exact same place. So let's go. So Google Earth is loading, and depending on your internet speed, it'll load faster or slower. Now, I was just searching for Mount Everest. If you click the search button, you can type in whatever you want to find it. And Google Earth will zoom straight there. A couple things to note. As you're looking around the Earth, not only do you have what's on the screen, but on the very bottom right-hand corner, you can see the latitude, the longitude, the altitude of your cursor, and the altitude of the camera angle. So as we come on over here with the cursor to the tippy top of Mount Everest, we're at about 8,800-ish meters. And that is the height of Mount Everest currently measured. So let's explore a little more. Some other things you can do is over on the left side, you can hit measure distance and area, and you can draw a path. So a path is one dot. You can click, drag your cursor to click another dot, and if you double click it, it will end that path. So there you have the distance of that line you just drew on Earth. You can change your units if you would like, but we'll stick with meters or maybe kilometers. If you don't like it, you can restart it, you can copy it, you can do whatever you want there, but we don't really need that. So back to the next things that we can do with Google Earth. If we zoom out, so that's hitting this minus button, we'll zoom out and zoom out and zoom out. Now, Google Earth is covered or is showing satellite images all over the Earth. And with the satellite images on land, we can see mountains as the snow-capped mountains as white on the top. And then as we look into the oceans, we're looking at the bathymetry, the depth of the oceans. So lighter oceans, seafloors, are light blue until we get to our deepest, darkest blues and the deepest depths of our oceans. So that's a way to see some of the elevations both on land and underwater. So if we scroll around and just take a look at what we can see on Earth. So you can see we've got the Rocky Mountains up into the Cascades. We can go all the way down and follow that continental divide until we get to the Andes in South America. We've got over in New Zealand, you can see that range across on. And on to the next part of this. So let's take a look between South America and Africa. And without even drawing a path to really see the bathymetry, we can see that going from the coast of South America, so off the coast of Brazil, we have above sea level, and then we dip into sea level, and then pretty narrow continental shelf. We go deeper down until we get to around the middle. If we zoom in closer and closer and closer, you can actually start seeing the elevation below sea level. So it varies a little bit, but pretty much 5,000 meters below sea level until we get to around 2,000, 3,000, and continue on back to 5,000 or 4.5 at least, and then come to the continental shelf of Africa. So getting much shallower and shallower until we're back onto land again. So if you wanted, you could draw out a graph of the distance below sea level, or that elevation below sea level. Bathymetry is what we call that. Let's try that on the other side of South America. So crossing South America, you can see we've got about 800, 700, 400 coming across the Amazon and continuing to come pretty low there. And continuing those lowlands until we get quite steep into the 2,000, 3,000, 4,000, 5,000 meters above sea level as we cross those Andes, and deep down, so 4,000, 1,000, until we get to sea level, okay, right at that coast. We drop down rather quickly, negative 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, negative. So we kind of top out at around 6,500-ish. And then quite quickly come back out. So 4,000. Whoops, zoomed in. Let's zoom back out. Doot, doot, doot. And stay pretty steady at around 4,000 all the way on out. Okay. So there we can see the bathymetry off the coast of the western coast of South America. There's that very definite trench. So let's take a look now at Challenger Deep. We're going to fly on over to that and zoom down into the depths of that trench. This is the deepest trench in the entire world. So it's a depth of negative 10,900 meters, almost 11,000 meters below sea level. So we can zoom out and just see how deep that blue is. So it's between Guam and just north of Guam, off the coast of Papua New Guinea, pretty close to the Philippines. Whoops, not north of Guam, because we are turned around here. And zoom back in. All right, there we go. So there's our perspective, just south of Guam. And if you zoom around, you can take a look at other areas. So we've got a trench off the coast of the Philippines, off the coast of Indonesia. We have other trenches. Well, we already talked about this one off the coast of South America, but we've got one across Central America. We've got them across the Caribbean. So all different places all over the earth. Off the coast of the Aleutian Islands in Alaska and Japan. So now let's take a look at where some of the earthquakes are going on. To do this, you need to look at the earthquake layers. So to add a layer, you're going to click on Projects, New Project, and then import a KML file from, in this case, my computer. All over the world. Notice how these earthquakes are coming in different colors. So between South America and Africa and North America and Europe, they're pretty much all oranges of one form or another. And if we look at that legend, we'll just take a look at all of these. These oranges mean that we're relatively shallow earthquakes. Whereas if we come to a trench, for example, we have oranges to yellows to greens to blues to purples to reds. If we look at other trenches, we see that same kind of pattern going. Other divergent boundaries, we have pretty much just oranges. If we come over to the other side of the world, another trench, we've got that orange to yellow to green to blues. So this is a pattern that's repeating all over the world with the depth of earthquakes. And when looking at those patterns, we don't have earthquakes scattered randomly all over Earth. We see them in those specific locations. And now let's look at volcanoes of the world. So if you click on there, we notice that a lot of these volcanoes are in quite similar locations as our earthquakes were. We have a couple scattered on the mid-ocean ridge, more concentrated on those oceanic, continental, convergent boundaries, some oceanic convergent boundaries. And then a couple just kind of scattered in the middle. Not quite scattered, but concentrated in spots within the middle of a plate. So if we take a look, for example, at Iceland, not only is Iceland in the middle of a divergent boundary, but it is also over a hot spot. So there are a ton of volcanoes all over Iceland, some of them quite active. So let's look at where those plate boundaries are. Again, if we draw that in, we've got that divergent boundary, those plates moving apart from each other at Iceland, all down that mid-Atlantic ridge. We have the Somali plate ripping apart from the African plate at our Great Rift. We have some mid-ocean ridges, and then all those trenches where we have one plate subducting under another. So the Australian plate subducting under the Sumatran plate, which is a minor plate, or the Philippine plate subducting under the Eurasian plate. So now let's look at the plate boundary between Africa and South America. So let's scroll on over here. And we can see we've got a divergent boundary. So in a couple places, even though for the most part we've got South America moving apart from the African plate, there are a couple spots where it's more of a transform boundary. But overall, if I zoom out here, there's more green than red. So now let's travel westward across the South American plate relative to in the Nazca plate. So here we've got that Nazca plate and the South American plate. And you can see that that Nazca plate is subducting under the South American plate. So think if you didn't have that plate boundary layer, I'm going to turn that earthquake layer back on. How could you figure out where that plate boundary is? What clues do you have on the map? So here we have the earthquakes along with those volcanoes, and you can see the bathymetry. So a little bit of everything right now. But now we're going to turn on the age of the ocean floors. So if we look at the age of the ocean floors, I'm going to open up this layer and open up those isochrons, those 5 million year isochrons. Take a look. So we've got 0, our very newest seafloor, to 30 ago, to 120 million years ago, 250 million years ago. So again, each one of those lines drawn is 5 million years. So on average, continental crust is about 2 billion years old. And in fact, the oldest rocks on Earth are about 3.8 billion years. And some of the grains of these rocks are even older than that. So the age of their very oldest seafloor is around, if we zoom in here, so we've got this dark blue, so 150, 55, 60, 75, 80, 85, 90, so about 190 million years old is this rock right off the western coast of South America. A few places, Mediterranean looks a little bit older than that. So if we look at the Pacific plate, we don't see a lot of those greens and blues and almost purples over here. So the Pacific plate, or at least this Nazca plate off the coast of South America, is much younger. So Easter Island is right here, pretty close to this spreading center between the Nazca plate and the Pacific plate. Whereas the Hawaiian Islands are right in the middle of that Pacific plate. So they don't look connected. There's got to be two different processes that are forming these islands. So I'd like you to think about some of the questions in your document and be prepared to ask me with anything that you're still wondering or anything that you noticed that you have questions about. So thank you for following me and exploring plate tectonics with Google Earth.